Hey everybody, it's Mr. N, and we are going to do some Riemann sum problems that have tabular approximations. So this is kind of like how you see some of these questions on the AP test. So let's take a look at this. The first one says, UPS delivers packages between 9 a.m. and 7 p.m. At 9 a.m., we're going to assume that's the starting. We'll call it t equals 0. And 7, we'll say that that's 10 hours later. So we'll call that t equals 10. The number of packages delivered t hours after 9 a.m. is modeled by a differentiable function, p, for which t is in between 0 and t is in between 0 and 10, and p double prime of t is greater than 0 for all t. Values of p of t in thousands of packages at various times are shown in the table below. So we've got this table. So at 0 hours, 0 packages. That makes sense. 5 hours, 3,000 packages. 6 hours, 4,000. 9 hours into it, there's 6,000 packages, and at 10, 11,000 packages were delivered. Okay, use right Riemann sums with 4 subintervals given by the table to approximate the integral from 0 to 10 p of t dt. What does this answer mean? So the first thing that we want to do when we see these problems is to kind of quickly sketch a quick rough graph as to what's happening. So I'm going to do that right here, and I'm going to have some points here. We've got 0, 0. Now, this is a rough sketch. Over here, we're going to say 5, and we'll call this 3 right there. Then we're going to say 6, and we'll be up at 4. And then my next point is over here at 9, and we're going to say that this is 6. And then my last point over here is at 10, and we are up here at 11. So 9, 6, I forgot to put the dot. There we go. So basically, I've sketched some points. Now, since it's differentiable, we know it's continuous, so we don't have to worry about that, and we know the second derivative is greater than 0, so it's concave up the whole time as well. So use right Riemann sums with 4 subintervals. So to use a right Riemann sum here, I would need to make right rectangles like that. Notice I didn't use this point right in here because I need to use the right point. And we have 4 subintervals. So I should be able to make 4 out of these. If not, I'll have to adjust it, but right now there's 1, there's 2, there's 3, and the right would be 4. Okay, so those are my 4 rectangles. And we have to approximate this from 0 to 10, and that's the area under the curve, right? Because that's what we're doing when we approximate these. So now we have the area equals the sum of the rectangles that I make, or that I made, which is the sum of each delta x times the height. Now this is the delta x. Notice the delta x is not uniform. On the first one, the delta x is 5 right here. On the next one, from 0 to 5 is 5. On the next one, the delta x is 1. The delta x is 3. The delta x is 1. So I need this width times this height. So basically, I'm just finding each rectangle separately. There is no set formula for this. I have to find each rectangle for the base times the height, which is the delta x times h. So that's what I'm doing. So over here, I'll end up with the first one has a delta x of 5 times this height goes up to 3. Plus the second one, delta x is 1 and it goes up to 4. Plus the next one, delta x is 3 and it goes up to 6. And then the next one, delta x is 1, and it goes up to 11. So those are all my rectangles over here. So this gives me 15 plus 4 plus 18 plus 11, which gives me 48 square units. But what does that mean? Well, that's 48,000 packages total delivered. And that's what the integral from 0 to 10 of p of t dt means. Okay, 48,000 packs. So it's a total number. I can write it over here again to explain it. Total number of packages delivered from t equals 0 to t equals 10. And it's that right there. All right. So let's move on. Let's take a look at part B. What does part B ask? It says, same thing, trapezoidal sum. This time we need to use trapezoids from 0 to 10. So I'm going to redraw this down here, this quickly sketch this graph again down here just so that we know what's going on. There's 5, there's 3, there's 6, there's 4, and we got 0, 0, I forgot to put that one. Then we've got 9, and up here at 6, and then we've got 10, and we're up here at 11. So we've got these points like this time. Okay, it doesn't matter, again, it doesn't matter if the sketch is perfect. We are just sketching approximation of what's going on. So over here, this time we're using trapezoids. So for a trapezoid, the area is going to be the sum of the traps, right? And the area of a trapezoid is going to be 1/2 times the height, times the height times the sum of the bases. Now, our height will be our delta x. So this will be this first trapezoid, the second trapezoid, the third trapezoid, the fourth trapezoid. Okay, there's your 4 trapezoids. So this is your delta x, which is our height, really. This is base 1, that's base 2. Then this is the next base and the next base. So the sum of the bases, or the sum of the areas, is going to be the total area of this trapezoid. So putting this into a formula, the area is going to be 1/2 delta x, and then we need base 1 plus base 2, etc., right? So the area is going to be 1/2 delta x. Now let's look at how we do this. We've got f of 0 for the first, let's put 1/2, let's put in what delta x actually is in this case, and our delta x over here is 5, right, for this first one. 5 times, now the first base is going to be f of 0. The second base will be f of 5. But we're going to use that twice, right, because it gets used here for this first one and the second one. Let me repeat why we're doing this twice. This first base and the last base only get used once for the trapezoid. This base right here gets used in this trapezoid on the left and this trapezoid on the right, so it gets used twice. So we put 2 in the middle of our equation there. So I'm going to go ahead and, instead of saying f of 0, I'm just going to go ahead and put in our heights right now since we know what those are. So let's go ahead and do that. So this is going to be a height of 0, plus, I think it'll be easier for you to understand, plus a height of 3. My next delta x, so I'm going to do it this way instead of the 2 times right now, because my delta x is not uniform. And then I'll go ahead and show you something. Okay, so the next one is going to be 1 as this, and then my 2 bases are 3 and 4. 3 plus 4. Then the next one is 3 again, has a width here of 3, and my 2 bases are 4 and 6. And then the next one has a width of 1, and my 2 bases are 6 and 11. Okay, I add all this up, and I'll get 34.5 thousand. Let me show you something else, though. Let me show you another little thing here. Remember how we said that 2 times method? You need to be really careful with that. That's great when everything's evenly spaced, but when it's not evenly spaced, what ends up happening is, suppose you did 1 times this and 2 times the ones in the middle, like in the formula. Well, look at this height is getting multiplied, right? It's this 3, f of 5. This is the f of 5, which is 3. On this one, it's getting multiplied by 5, but yet on this one, it's getting multiplied by 1. So you can't say 2 times just that value, and that's because it's not evenly spaced. So you're going to get something completely different. So you need to be careful. When they give you table ones like this, just always graph them out. Find each trapezoid on its own. Don't try to do shortcuts because it'll kind of mess you up. You could get around it, but just this is my recommendation. Just do it this way, and it'll keep you from making big mistakes. So again, my method here that I did this, I found the area of each one of these trapezoids separately. The 1/2 is because they all have that half in common. So all I did was length times base 1 plus base 2. This width, this width, delta x times base 1 plus base 2. This width times delta which is delta x times base 1 plus base 2, etc. Okay, so that way I kind of kept things consistent. Now let's do a midpoint Riemann sum. All right, I'm going to quickly again just sketch it so we know what we're looking at. We got 0, 0. We got 5, 3 right here. We got 6, 4. We got 9, 6. Yes, there is a way to cut and paste that graph, but I think it's going to take too long. And we got 10, 11 right up here. So that'll be that point. 9, 6 was this point. Midpoint. So here's what I'm going to do for midpoints. The midpoint between 3 and 5, or 0 and 5, is at 2.5, right? So that'll be right here, but that looks like, how high? I don't know how high up to go. This grid is not precise. You would have to do this on really good graph paper to get a precise answer, and so I'm not going to do that. And since we can only estimate the midpoint, our values will be just approximated on the y. Okay, so the area, when I draw this first one, okay, this first rectangle will look like that because there's the midpoint. So this will be a delta x of 5 times a height of, we can say it's 1.5. I'm just taking a wild guess here. Plus the second one. I draw this. Okay, midpoint is right here at 5.5, and that height will be right there, right? You see that? So this is my rectangle that looks like this from this midpoint. So we are going to say that this is a width of 1, a delta x of 1, and a height of 3.5. Plus the next one. Okay, here it is. So right here, the midpoint between 6 and 9, 6 plus 9 divided by 2 would give you this spot right in here, which is 7.5. So we're going to estimate this to go up there. So our rectangle will look like that. So this width is 3, and the height is right up here about 5, I'll guesstimate. Okay, and then the last one right here, we've got the midpoint at 9.5, and so then this rectangle will look like that. And we're going to say that this has a height of somewhere, this delta x is 1, right? And it goes up to somewhere, we're just going to say 7. I'm just going to estimate it to be 7. So over here, I get 7.5 plus 3.5 plus 15 plus 7, which is approximately 33 square, so 33 thousandths. And again, this was a sheer rough approximation. If they did this on the AP test, what they would do is they would put like an extra column here so you could actually find midpoints. Or say between 5, they would make this say between 5 and 10. And then you can actually use a midpoint right there because you'd find them, you'd use this one, the middle value. You'd use the middle value. You could do it that way. So that's what they would end up doing. All right, and the last question here. Suppose we had 1 over 10 times this integral. What does this solution mean? Well, let's take a look. If I have 1 over 10, I'm going from 0 to 10, but then I'm dividing it by 10. So that means I'm taking an average value, right? So this yields the average value of P of t from 0 to 10. So the average number of packages per delivered, I should say, delivered per hour. If suppose we use the answer from part B, okay, so the answer in part B was 34.5, if I use this one, okay, then we can say divide this by 10, 3.45 thousand packages per hour delivered. So it would just give us delivered. It would just give us that average. Okay, let's move to the problem. All right, here we go. Passenger Jet fuel consumption rate in gallons per minute is recorded during a flight. A function that expresses a twice differentiable function c of time t, where c double prime t is less than 0 for all t. So double prime less than 0, so it's concave down. So a table of selected values of ct for the time interval is shown. What are we going to do? We're going to quickly sketch a graph of this. So here's what I got. I got this graph right here. And I've got some values, and let's put these values on there. 0, 10, we're going up to 100, so 0, 10, so that's why I put that right there. Okay, then we've got 30, and actually we're going 100 this way. We're going to 85 up. 30, 40. Then we come over here at 40. At 40, we will go up to 50, right there, 40, 50. Then the next value is 70, and I'm going to go up to 65. So 70, 65. And the next value is 80, and I'm going to go up to 70. And the next value is 100, and I'm going to go up to 85. Right there. So it looks like that. Okay, so using the correct units, explain the meaning of this and in the context of this problem. So it's the area of the under the curve, right? We know the basics of it. Area under the curve from t equals 0 to t equals 100. But really, what specifically does it mean? That thus, we'll say thus, it is the total fuel consumption from t equals 0 to t equals 10 in gallons. All right, for part B, approximate the value using the left Riemann sum. So I already have a little graph here. Let's just go ahead and do left rectangles. So I'm going to make my left Riemann sums. So the first rectangle, I start on the left side, I go like this. Second rectangle, start on the left side, go like that. And it says there's going to be 5. So if I continue this out, there will be 5. Start on the left side, right, and go like that. Left side like this. Left side like that. And there's 1, 2, 3, 4, 5 rectangles. Notice I don't use that last point. It's going to stay up there. So let's just add up each rectangle. So the area is the sum of the rectangles, which in our case is going to be, the first one has a width of 30 and a height of 10. The second rectangle has a width of 10, and so that's x is 10, and a height up at 40. The third rectangle has a delta x of 10. 30. I'm going from 40 to 70, and a height up here of 50. Then the next rectangle from 70 to 80 has a width of 10 and a height up there at 65. And then the next rectangle has a width of 20 and a height up there at 70. Remember, we don't use that last point, which was 85. So 300 plus 400 plus 1500 plus 6500 plus 1400. Add all this up, I get 10,100 gallons of fuel, and that's what's going to be used. All right. Is this an over or under estimate? Well, let's take a look. If I connect, remember, this is a continuous curve. So since it's continuous, if I were to connect this curve, notice I go like this, right? Let's go ahead and do it with this thinner one instead. And I go like this, okay? All this is gaps, all these gaps. So it'll give me an underestimate. And why is it an underestimate? Because it's increasing with left endpoints. Okay, next one, trapezoidal sum. Let's take a look at what we got here. Trapezoidal sum with 5 subintervals. I'm going to re-sketch this situation. So let me put this sketch here on the side, graphing from what they gave me in the table. Not sure if you can see the table. If I slide this down, you won't be able to see my graph. So I'll tell you what the values are. So the first one is 0, 10 again. So there, it's right here at 0, 10. We'll put a dot. The second one is 30, 40. 30, 40. You can probably fast forward this. 40 to 50, because all I'm doing is redoing this part. 70 goes up to 65. And then 80 goes up to 70. And then 100 goes up to 85 right there. Okay, now we want trapezoids. So let me connect this with trapezoids. And here are what my trapezoids will look like. Like this. There's my first one. There's my next trapezoid. Next one, and next one. I should have 1, 2, 3, 4, 5 trapezoids. Perfect. So let's see what we end up with. In this case, again, I'm going to, since these are not evenly spaced, I'm going to find each trapezoid on its own. So the area of a trapezoid, to remind you, is 1/2 times the height times base 1 plus base 2. And in our context, it's going to be 1/2 delta x. And then this will be f of, well, we'll just say base 1 plus base 2. So I don't confuse you with the 2's in there, anything like that. All right, so now for this, we will say the area is going to be 1/2. Now let's find each area independently, each trapezoid. So for the first trapezoid, my delta x right here is going to be 30, right? And the 1/2 is outside because it's 1/2 times everything. So, and then my base 1 and base 2, that's going to be 10 and 40. Plus the next one has a delta x of 10 times my base 1 is 30, my base 2, base 1 here is 40, my second base is 50. 40 plus 50. Now again, remember, it's different delta x's times these. That's why I'm not doing that 2 times thing. Okay, plus, and the next one is going to be delta x of 30, and I'll go up to 50 right here, and then 65. And then the next one will have a delta x of 10, and I'll go up over here. Delta x is 10. Over here it's 65. Over there it's 70. So 65 plus 70. And then the last one will be 20, and then 70 plus 85. And that's what this will look like. Let's clean this up. You get 1/2. And here I'm going to just multiply it all out. 1,500 plus 900 plus 3450 plus 13,500 plus 3,100. And this gives me an approximate value of 11,225 gallons of fuel used. Remember, we said the other one was an underestimate. This is more of a better, closer estimate. And yes, since it was an underestimate, this value should have been greater, and it was. So we did it correctly. All right, thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.